So I want to talk about a very particular infinite series that is going to look very strange when I write it on the board, but I'm going to do it anyway. Okay. That's a lot of symbols. You guys know what the exclamation point means, right? Yeah?
It means factorial.
Factorial, right. It doesn't mean you just yell the name, right? It's not that. Anyone know what the double factorial means? That might be new to you, so let me tell you what that is. Okay. So it's just shorthand. 2n plus 1 double factorial is, it's like a factorial, but you skip the even things. Right? So 5 double factorial is just 5 times 3 times 1, and 7 double factorial is 7 times 5 times 3 times 1. Okay? You just skip the even guys. Okay? Just shorthand. So what I have here is this very weird sum. I've got 4 to the n minus 1, n factorial, n minus 1 factorial, 2n plus 1 double factorial squared. Okay, where did this come from? It's interesting where this comes from, and we'll see why. We might actually care about the sum of this series. If I just wrote this on a quiz and asked you, does this thing converge, what would you do? Ratio test. Thank you. You would use something called the ratio test, which is a test that we use to determine if a series like this actually adds up. Now, the way that you actually do these is, you can't add up infinitely many things, right? I mean, you just can't. There's not enough time in the day or the year or the universe, okay? What you do, though, is you add up the first however many terms, like the first 10, okay? And then you add up the next term, and so on, and you get a new sequence. And then, if that sequence has a limit, we say that the sum converges. You probably know how to add up geometric series, right? Like that's something you learn at some point, probably in pre-algebra or something, right? I don't remember when you learned that sort of thing. Geometric series you're probably all okay with. Series like this are a little weirder. I won't run through the ratio test, but what do you think you get? You get a ratio of 1, right? So that tells you what? Nothing. Okay? So there are tests for determining whether or not these series stop somewhere, add up to something. The ratio test is everyone's favorite when you see factorials and things like that. And it turns out that if you get a ratio less than 1, the series converges. Great. If you get a ratio bigger than 1, the series doesn't converge. Great. If you get a ratio of 1, you just don't know anything. So here the ratio test fails. You get so the ratio, it goes to 1. So that's no good. Okay, great. Or not great, whatever. Fine. What's the next thing you do? Look, it's modern times. What do? You fire up Wolfram Alpha and ask. Right? I know what's up. I know what you guys do. You're not pulling anything over on us, you know. So you consult the oracle. So the 100th partial sum, meaning I add up the first 100 terms of this series, okay, you get is approximately equal to 0.212655381. Okay, the 1000th partial sum is approximately 0.214405657. Okay? So the ratio test failed, so I don't know if this thing converges or not. I add up the difference between the 100th and the 1000th term, you'll notice, is only about 2 thousandths, or 18 10,000ths. So, I mean, I don't know if this thing converges or not. But if it doesn't converge, it's going to take forever to get to infinity, right? I mean, I added up 1,000 terms, and I'm still only here. I've only changed the third decimal place a little bit. Okay. Again, it's not a proof; it's evidence. Okay. So I don't know if this thing converges or not. And often, you know, especially so if you haven't had Calc 2 yet, you'll learn about this when you start doing infinite series. You'll be asked, does this thing converge or not? And you have a whole flow chart of things that you try. And I even created one for my students years ago. And the flow chart at the end, you know, it's like if none of this works, just relax, go get a cup of coffee, just give up. Okay, I'm not giving up on this series. All right, and I'm not going to let you give up on it either. Okay, we're going to find the sum of this series. Okay, you with me?
Yes.
We're in? All right, good. Now, but I'm going to walk away from this for a while. So instead, I'm going to talk about fractals for a little while. Okay, so naturally, okay. My favorite fractal, or one of them anyway, is the Sierpinski carpet. So how does this work? You take a square, okay? So, and now I'm going to divide it into ninths. And I'm going to throw away the middle square. Okay, this is an iterative construction. So I started with a square, I'm going to throw away the middle. Okay, now I have these 8 squares left over. Okay, I'm going to divide each of them into 9 pieces, and I'm going to throw away the middle piece of each of those. Okay, now what am I going to do? I'm going to do it again, right? So in each one of these subsquares, there are now 8 little squares around this center square. And in each of those, I'm going to throw away the middle of that. Yeah, question? No? Okay. I do that in all of them. And so on. Then, in each one of these little squares, there's 8 squares, and you throw away the middle of that. Okay, you do this forever. Okay, what's left? You might say, okay, is there anything left? Sure, there's lots of stuff left. What's left is called the Sierpinski carpet. Okay, named after Polish mathematician Wacław Sierpinski, very famous topologist. Okay, what's the area of the Sierpinski carpet? I mean, I haven't thrown away everything, right? I mean, this is a pretty lousy carpet. I mean, you know, it's you can see through it, essentially, right? Like, you don't want to wipe your feet on it, you're going to tear it up, okay? But, so it's not 0, or is it? Let's find out. What have I thrown away, right? Sometimes the way to find the answer is to figure out what you've thrown away. Yeah?
1/9.
Okay.
1/9 and then 1/9 of the,
Yeah.
remaining, and then 1/9 of the remaining.
Right. So what have I done? So let's see. At the first step, so let's figure out what we've removed. What have I thrown away? So that's right. First I threw away 1/9. Okay. And then in each of the 8 pieces, how much did I throw away? Yeah?
8/18.
Is it 18 or is it?
Oh, 8/81.
81, right. 9 squared, because each one of these little squares has width 1/9. And then in each of these 8, there are 8, so there's 64 of things 9 cubed, right? So on inside each one of these little things, this is 1 over 81, right? Yeah, okay? And so on. So at the nth stage, I'm throwing away 8 to the n minus 1 over 9 to the n. Right. This is a geometric series. You guys remember geometric series? You know the sum of a geometric series? Do you remember how this works? What is it?
First term.
It's the first term divided by 1 minus the ratio. And the ratio is 8/9. What is that?
1/9 over 1/9.
1/9, which is 1.
I removed everything. Except I didn't. There are lots of things left over in this set. This is one of these, I'm not going to go into the weird infinity side of this talk, okay? That would be another talk, okay? But there are infinitely many things left over in this set. In fact, lots and lots of infinitely many things are left over in this set, right? However, the total area that I've removed is 1. So the area of the Sierpinski carpet is 0. Right? Okay, is your mind blown yet? Okay. So while I'm here, let's just talk about fractals a little bit while we're here, okay? Now, I promise you, fractals have nothing to do with this, but the Sierpinski carpet does, and I'm going to come back to that. Okay, but let's just talk for a second about fractals, because I thought this would just be something fun that you should know, and then you can wow your friends with it. So we say that a set X is self-similar if there is a subset S that is similar to X. And so, in particular, this means that X is the union of a finite number of copies of S. And then there's a scaling factor. Okay, so I'll draw you plenty of pictures here in a minute. Okay, associated to it. By that I mean you've got your object X, and you've got a subset, okay, that's similar to it. What that means is you scale that thing up by a certain size, by a certain amount, and you get the thing. Okay, so examples. So the simplest example that we can look at is an interval. So you take an interval, doesn't matter how long it is, but you divide it into n pieces, n even length pieces. Then each one of these pieces is similar to the entire interval. And what's the scale factor? Well, I have to scale each piece up by a factor of n to get the whole interval. So the scale factor here is n pieces for an interval. What about a square? Let's say I take a square and I divide each side into n pieces, so that I've divided the whole square into n squared pieces. Now, that's how many, each one of these little squares is, of course, similar to the big square. Now, what's the scale factor? Your instinct might be to say that it's n squared, but that's not exactly what's going on. What do I have to do? I have to scale each of the side lengths by a factor of n. So the scale factor in this case is n, and there are n squared pieces. Okay, so these are two simple examples. So this leads us to a definition. The definition here is of the fractal dimension of a self-similar set. So if X is self-similar, and if I have a certain number of self-similar pieces, and then I have the scaling factor associated to those pieces, the fractal dimension is defined to be the logarithm of the number of self-similar pieces divided by the logarithm of the scaling factor. Okay? So why is this a good definition? Well, I mean, whenever you have such a thing, you should want to check it on your earlier idea of what you think dimension is. So let's take a look at this interval again. Intervals are one-dimensional. We think of them, they're like a line. Well, what's the fractal dimension? So we have n self-similar pieces. The scaling factor is also n, and therefore the fractal dimension is log n over log n, which is 1. What about the square? Well, we have n squared pieces, and the scale factor is n, so the fractal dimension of that is the log of n squared of the log of n. Log of n squared, of course, is 2 log n, so I get 2 log n over log n, which is 2, which agrees with our idea of what the dimension of a square is. Okay? So this definition, while we'll have to see how well it works with, with other objects, at least makes sense for our notions of traditional things. So next example I want to show you is the Cantor set. So what you do to get the Cantor set is you take the interval and from 0 to 1, and you delete the middle open 1/3, between 1/3 and 2/3. Okay? And then you, each of these two subintervals, you delete the middle third out of each of those. So now I have 4 pieces of length 1/9. And then from each of those, you delete the middle third out of that. And then I end up with 8 pieces of length, what is that, 1/27th, I guess, and so on. You just keep iterating this process, so on and so on and so on. And what's left over is
the Cantor set. Now, this is everybody's sort of favorite fractal object. It's an uncountable set, which I'm not going to talk about in this lecture, but it's a very interesting thing. One way to think of these are the numbers. If you wrote the binary expansion of these numbers, so binary decimals, sorry, not binary, base 3 decimals, you would only use the numbers 0 and 2. You wouldn't have any 1s. I want to think about why that's true.
What's the dimension of the Cantor set? Yeah.
1.
You want it to be 1, right? But let's see. Let's try this calculation. So can you find a subset of the Cantor set that is similar to the whole thing? Yeah.
If you take any of the not the middle third, but the first third or the last third, it's similar to the whole thing.
Right. So this chunk, right, is similar to the whole thing because it's just a scaled down version. I just keep iterating this process. So, and in fact, that's true for any one of these. Even this little guy here is similar to the whole thing. And then the little thing in here is similar to the whole thing. But I like this idea of, let's just take this. So how many pieces are there?
2.
2, right? There's this one and there's this one. How much do I have to scale it up by? Yeah.
By 3.
By 3, right? This is 1/3 the size of that. Which I should know what this number is, but 0.6309. Okay? So it's not 1, but it's also not 0, which kind of makes sense, right? It's not everything. It's not the whole line. It's sort of part of a line. It's like dust all over the line. And the dimension is 0.6309, log 2 over log 3. Okay? So that's why I like this definition, because it works fine for the things that we think it works fine for, and it allows us to extend an idea of dimension. This thing, it can't be one-dimensional. It doesn't fill out the line, so it shouldn't be one-dimensional. But it's also not nothing. 0 dimensions is a point, and this thing is clearly spread out all over the place. It's not just 0. Okay? So that's a fun one. How about, well, the Sierpinski carpet is up here. What's its dimension? We'll just do that real quick, since I have a picture. How many what's my sort of nugget of self-similar piece?
8.
There's 8 of them, right? And what's the scaling factor? Yeah?
9.
It's 3, right? You got to scale in each direction. 3. So that is, what is that? 1.8928 and some change. Okay, so it's not 2-dimensional, but it's more than 1-dimensional. Okay, good enough. What are your other favorite fractals? How about, yeah, how did you know? Did you see my picture? You're cheating.
I just like the Coke snowflake.
You saw my picture. I know what's up.
I did not.
So the Coke snowflake is a lot of fun. So how do you get the Coke snowflake? Well, what you do is you start with an equilateral triangle, okay? And then you take each side and you remove the middle third, and then you plunk another equilateral triangle with that base on there. Okay, so now these are gone. So it's sort of a Star of David looking thing after one iteration, okay? And then you just iterate this process. So now on each one of these sides, you chop out the middle third, but you do it on every side, okay? And you keep going, okay? So this is called the Coke snowflake. Well, the scaling factor is kind of easier. What do you think the scaling factor is? Yeah?
Scaling factor is
3, right? I'm taking each side, and this guy is sort of, if you triple this thing, you get the whole thing. Okay, so the scaling factor is 3. What's the number of self-similar pieces? Yeah.
Aren't aren't there none? Because if you take like each of those kind of arms,
Mm-hmm.
the bottom half part is erased, and on the whole thing, not the whole bottom part is erased.
Okay, well let's before we decide whether or not that's correct, what would that mean the dimension is?
Not like it will be over log 0, which is just wait no. It
No.
will be log 0 over.
No, you said 9, right? So it'd be log 9 divided by log 3, which is what? 2. Does this seem like a two-dimensional object? No, it's just a curve. Should be less than that, right? It should be a little more than 1, but not quite 2, because it's a curve. I'm not counting the interior. I'm just sort of thinking of the boundary curve as the object. Yeah, that's the tricky thing. So it ought to be somewhere between 1 and 2. Well, the answer here is 4, and it's not so obvious to see, but what's going on at each stage, what you're doing is each edge is getting replaced by 4 things, right? So in other words, you've got this whole thing, and when you're done doing the iteration, you have 1, 2, 3, 4. Okay? When you do it here, you start with one thing, and when you're done, you've got 1, 2, 3, 4. Okay? So it's actually 4 is the self-similarity ratio. That one's tricky. That's weird. That's why. So that means the dimension is log 4 over log 3, which is whatever that is. Some number, 1.2619. Okay, so a little more than 1. And then one more. So there's a triangle version of the Sierpinski carpet. It's called the Sierpinski triangle. So you take this guy, you remove that, and then out of each one of these, you remove that, 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 and so on. Okay, you have a similar sort of thing. So now, what's the dimension? How many pieces are there? Yeah? 3, right? What's the scaling factor? 2, which is whatever this is. Okay. So different from the Sierpinski carpet, even though it's the same sort of iterative process, right? Instead of taking a square and removing the middle ninth, I'm taking a triangle and removing the middle quarter. The area of this thing is still 0, of course. Okay. Different dimension, though. That's kind of fun. One other thing about the Koch snowflake, how long is it? What's the perimeter? It's infinite. Yeah. So the perimeter keeps growing. So, you probably heard the question, how long is the coastline of the United States? What's the answer? Depends on how long of a ruler you're using, right? So with the Koch snowflake, this thing sort of got infinitely much perimeter in here, but you can't see most of it. Like when you stand back here, it looks like this. You have to zoom in and zoom in and zoom in and zoom in to see those little jagged things, right? So with my ruler, if my ruler is only this long, I'm going to get an answer, okay? So same deal with the coastline of Florida, right? I mean, how long is it? Well, it's infinity if you allow yourself an arbitrarily small ruler. But in practice, of course, we use, a ruler. Well, not really. Right? I don't think anybody's going to walk around Florida with a ruler. But the area, of course, is finite. Infinite perimeter, finite area. In fact, the finite area is sort of fun, I'll tell you. If the original side length here was 1, then this area is 2 square roots of 3 over 3. That's kind of fun. Okay. All right. Any questions about fractals? It has nothing to do with the rest of the talk, but I wanted to introduce Sierpinski carpet. Yeah.
So for the number of self-similar
Mm-hmm.
things on the Koch snowflake,
Mhm.
I can see 3 of them. Can you point to me where the 4th one is?
Yeah, so each side, so here's what you're doing. You've got a side, okay? And what you're doing is you are taking this one piece and you're throwing away the middle and you're popping in that. So now I've got 1, 2, 3, 4 pieces.
Oh, I see.
That's why it's 4, yeah. It took me a minute too. Like when I was sitting here thinking about it, I mean, when I was writing up these notes, I was like, well, yeah, what is the similarity factor? Because I wanted to say it was 3, but I knew that wasn't right because the scaling factor is 3, and this is not one-dimensional. Yeah, it's 4.
You're not really looking for triangles. You're looking for
No, you're looking
triangles.
for, yeah, that's right. How much you replace it by,
Would
yeah.
it be like 4 for each of the 3 different edges?
Yes, but they're all the same, right?
Okay.
Yeah, so in other words, this edge and this edge, yeah, that's all the same. So, yeah, so in other words, this thing, you can cover it 4 times, essentially. That's the way it goes, yeah. You can cover it up by 4 times. Okay. Well, that was just a fun little aside. But I started with the Sierpinski carpet because I wanted to do something else. So instead of the Sierpinski carpet, I'm going to introduce something, and I'm going to call it the Wallis Sieve. It's not a carpet, it's a sieve. You guys know what a sieve is, right? Okay, it's like something that strains, like a colander, like you know, your strainer for your noodles. That's an example of a sieve. It's something that lets things pass through. All right. Same setup. I'm going to start with the square. Okay, and I'm going to divide it into ninths. And I'm going to throw away this middle square. Okay? But now the next thing I'm going to do is the following. So in each one of these 8 squares, now for the Sierpinski carpet, what did I do? I divided it into ninths and threw away the middle thing. I'm not going to do that this time. I'm going to divide it not into ninths, but into 25ths. Okay? Do that for all 8 of those. And now I'm going to remove this middle square. Okay? All right? So now, how big is each one of these? Let's see, so it's 1/25 of 1/9, right? So it's 1/9 times 25, okay? Whatever that is, 1/225, whatever, who cares, okay? Now, in each one of these guys, now I'm going to divide these into what? 1/49, right? So I had thirds, and I'm going to do fifths, and I do it into sevenths. And I remove the middle square there. Okay? So this is a 7 by 7 subdivision. And I remove the middle thing there. Okay? And I do this forever. So I'm not taking out as much. With the Sierpinski carpet, you know, I took out a lot. I took out a third, and then I took out a ninth, and I took out a ninth, and then an 81st or whatever, and kept doing that. This time, I'm starting big, but at every stage, I'm taking out something smaller than what I took out at the previous stage. Okay? You with me? Different sort of object. Not really fractal anymore either. Like, it doesn't scale up. I can't really talk. It's not self-similar anymore. It wants to be, but it isn't. Okay. What's the area?
I think saying 0 would be too easy.
Pi over 24.
Pi over 24? That's not crazy, actually. I don't know. Did you mess up? Well, I don't know. So what's the area? So after the first iteration, all I've removed is this 1/9, right? So it's 8/9 after one iteration. Okay. But after the second iteration, well, okay, in each one of these 8/9, what do I have? I have 24/25, right? I keep those. And then after the third iteration, in each one of these, I have 48/49. Okay, and then the next one, I guess, is what, 80/81, right?
Or no, it's 63/60. Or, yeah,
Nope,
so it's
9.
odd. It's
Yeah,
odd.
take the odd numbers. Okay, so I'm getting this infinite product. That's the area of this thing. Okay, so let's break that up a little bit. This breaks apart a little bit. So 8/9 I'm going to write as 2/3 times 4/3. And then 24/25 is 4/5 times 6/5. And the next one is 6/7 times 8/7, and so on. The general term out here is 2n over 2n minus 1 times 2n over 2n plus 1. Okay? Infinite product. And I'm going to rewrite that in the following way. Starting at n equals 1, I have, if I write this product like this, forget the 1/2 for a second, that means 2 over 1 times 2 over 3. Well, I've got the 2 over 3. The next term is going to be 4 over 3 times 4 over 5. Okay? But I've got an extra 2, so I need to divide by 1/2. That's it. Okay? So this thing actually has a name. It's called the Wallis product formula. Anybody know who Wallace was? You've heard of Newton, right? Wallace was a little before Newton. English, figured some stuff out. You know, Newton really was the heavy hitter with calculus, but there were some pretty serious people before him. Wallace introduced the infinity symbol. Yeah, that's right. Yeah, so very influential guy. You know, Newton once famously said that, you know, if I've seen farther than others, it's only because I've stood on the shoulders of giants. He was talking about people like Wallace and Barrow, his advisor, and things like that. So this thing actually has, you can evaluate this. It's actually not so hard. So when you go home, if you're bored later, look up the Wallace product formula. There's a proof of it on the Wikipedia page. There's a wiki page for it. Just read it. If you know a little calculus, you can understand it. There's probably a non-calculus proof. There must be. I can't remember, but there must be. So anyway, what's interesting about this is that it actually can be evaluated, and the answer is pi over 2. That infinite product is pi over 2. So the answer to what is the area of this thing is pi over 4. So someone said pi over 24. Where'd you come up with that?
Oh, I just like wrote it out as a polynomial and then did something.
Okay. Sure. You know, only being off by a factor of 1/6 is pretty good. Like why pi would show up. Why does pi show up? That's weird. Why does pi show up? Like pi usually, if pi's showing up, it's usually a circle somewhere, right? Why is pi there? Interesting. Okay. Anyway, you evaluate this essentially by doing some trick with integrals of sines and cosines, and it all just sort of drops out that way. Okay. So the area of this thing is pi over 4. Okay. I'm lost. What are we doing? Oh, we started with that.
Series.
Some fractal that has that as its area.
Well, I don't know. Like when we figured out the area of the Sierpinski carpet, what did we do? We went at it indirectly, right? We started by figuring out how much we removed and added up what we removed, and we got 0. Okay. Now here I figured out this area. I wasn't adding anything. I was multiplying. Okay. So what if we tried that approach, the subtraction approach, to this guy? Like, what if we start figuring out what we're throwing away? So what are we removing? All right, so what? We removed a 9th first, right? That we got. At the next step, what do? I have 8. Okay.
25th of a 9.
Over 9 times 25.
Looks like that.
Okay. Yeah, all right, let's see. At the next step, I'm removing, so I have 8 times, around each one of these things, there's what? There's 24. And I'm removing 9 times 25 times 49. Can we do one more? times 48 over 9 times 25 times 49 times 81. Okay. So I hope you see in the denominator, these look like those double factorials squared, right? 3 squared, 5 squared, 7 squared, 9 squared. 3 squared, 5 squared, 7 squared. Okay. Is the numerator what I want it to be? Well, I don't know. I don't see it immediately. But look, I'm claiming it should be something like 4 to the n minus 1, n factorial, n minus 1 factorial, over 2n plus 1, double factorial, squared. Can we see how that works? And can we make that work? Let's see. This is, I've got a 4 in each one of these factors. So this is like 4, 1, 2, 3. I want to get an n factorial and n minus 1 factorial. So can I make this work? If I can convince you in one case, you'll probably believe it all the time, right?
Mm-hmm.
That's how this works, right?
Obviously.
I don't believe in proof by example, but sometimes just showing you one thing, you go, well, okay, it must be right. So, so this should be, so this is n equals 1, n equals 2, n equals 3, n equals 4. Okay, so let's see if this works. Can I make this look like 4 cubed times 4 factorial times 3 factorial? So how many 4s do I have here? I have 4, 4, 4. So let me pull a 4 out of each of those. So that's 4 cubed. And then what I have left is 2 times 6 times 12. Okay, so that's 4 cubed times, well, 12 squared is fine, but I don't really want that. I want a 4 factorial, which I have, 12 times 2, 4 factorial, times 3 factorial. Okay, it worked one time. So, okay, so this is exactly the series that I was interested in. So that's what I've removed. So what's the sum of this series?
1 minus pi over 4.
1 minus pi over 4. Let's find out. Am I right? Remember those numbers I threw up at the beginning? Like the 1,000th partial sum Wolfram Alpha told me was like 0.221 whatever. So let's see. What does my calculator say? Pi divided by 4 plus minus plus 1. 0.214601836, blah, blah, blah. Those numbers I threw up at the beginning, that was roughly it, right?
Mm-hmm.
So sometimes you can get to interesting places by taking weird detours. Okay. Any questions? I've just bullied you. You're done. Yeah. What's up?
This isn't a real question, but is there a mathematically rigorous distinction between a sieve and a carpet?
No. It's just the carpet. I mean, it's flat.
Its area is 0.
Its area is 0. It's
Doesn't cover anything.
kind of doesn't cover anything except it covers the.
It's more like just a patchwork of threads.
In other words, yeah, it's a very threadbare carpet. Whereas the sieve, the holes are bigger, right? So the fact that there's area to this sieve is kind of not surprising because we're just not taking away as much. And look, let's be honest. I mean, this whole business of infinite series and something like that, it's getting to the business of infinity, which is very slippery, right? What we mean is, in the end, in the limit, right, we've removed everything. We've taken away, something of area 1. But at any finite iteration, of course, there's stuff left over. Okay, so in that set of things in the Sierpinski carpet, there's plenty of things there. It's an uncountable set. There's infinitely many guys in that set. It's just that they're kind of sprinkled out like dust, just like the Cantor set. It looks like I've removed everything because the stuff that I've removed adds up to 1, but there's lots of stuff sprinkled across there. So yeah, it's like a very threadbare carpet. That's the way I would describe it. You sure? Yeah? Okay, one more.
Back with your definition of X is self-similar,
Yeah,
where you say it's a
that's a fuzzy definition, by the way, but yeah.
a
Yes.
What does copies mean?
Meaning identical copies. So, so for example, this, the interval, if I chop it into, say, 4 pieces, this thing covers this. I mean, pretend I drew this evenly. I can take this thing and take 4 copies of it and completely cover the thing. So the Sierpinski carpet, for example, I can take this thing, and there are 8 of them, and I can cover the whole thing with it.
I
Okay?
guess the reason I ask is
Yeah.
with the intervals,
Yep.
it's not the same interval exactly. Like it's a different set. It's a different.
It's a different set. Okay, right. So these 2 sets, though, are, the technical term is isomorphic or homeomorphic or whatever you want. Well, I'm going to be careful, because this set is homeomorphic to the whole set. But so a similar piece is homeomorphic to the whole thing.
I was
But
going to ask isomorphic, but I didn't want to
but
say something wrong.
but these things are isometric would actually even be the right word, because they have the same length. Right. So if you want to start getting into geometry questions, you tend to use words like isometry, which means distance preserving. Okay. So this set is isometric to this set. Pretend they're the same size. I just can't draw. Okay. These 2 things are isometric. This guy is homeomorphic, or isomorphic if you want, to the whole thing, but it's not isometric because this length is different from that length. Okay. So similar things are homeomorphic without being isometric, because you have to scale. That's where the scaling factor comes in. Yeah. Sure. Anything else?
Thank you very much.
Yeah.